Well guys, this is going to be a really interesting video for you. This is Points of Inflection Part 1, where I do all the conceptual stuff, and Points of Inflection Part 2 is going to be where I give you some actual working maths to do with this stuff, okay? But the concept is the most important bit. Once you get the concept, everything else falls into place, okay? So, what is a point of inflection? Well, we're about to find out. A point of inflection Points of inflection are a direct application of second derivatives. At a point of inflection, the second derivative is equal to 0, and it crosses over. That is, the second derivative crosses over from positive to negative, or vice versa, through 0 at the point of inflection. What a grip, eh? Now, in order to understand this, I think we probably need to firstly look at the concept of the rate of change of the gradient, which is what you mean by the second derivative. That is the rate of change of the gradient of a function. Okay, so we've got d by dx of dy dx, which is d2y dx squared, which is the second derivative of y with respect to x, yes? In practical terms, it means the instantaneous rate of change of the gradient at a point x, okay? You get that? Let us therefore examine the rate of change of the gradient of a function. We better pick a function and have a look at this. And I've picked y equals x squared and y equals minus x squared, okay? Let's just see what we get. Therefore, dy dx equals 2x, or in the case of this upside down one, dy dx is minus 2x, isn't it? Now, d2y dx squared, or d by dx of dy dx equals 2, and in this case, with the upside down one, it's minus 2. Now, what is that telling you? What is that telling you? That constant there, equal to 2. It's telling you that the rate of change of the gradient is constant. The rate of change of the gradient is constant. And for every 1 plus 1 increment in x, the gradient of y equals x squared goes up by 2. That's in the case of this one here. For this one here, what do you think? Well, the rate of change of the gradient is constant, and for every plus 1 increment in x, the gradient goes down by 2 in that case. Now that's pretty interesting, isn't it? That's what's going on. You see, the rate of change of the gradient for y equals x squared or y equals minus x squared always changes for every 1 increment plus 1 increment in x. It changes by 2 units. In this case, up by 2. In this case, down by 2. So the rate of change of the gradient is always 2. Okay? Now here are the graphs. Here they are, right? Here are the stars of our show for the moment, right? This one is plus x squared. This one is minus x squared. Now let's have a look. This now there's y equals x squared. There's a table of values. Okay, now let's go. There's x squared. X squared. Do you agree? Good. Now we're going to do dy dx now. Okay, that's 2x. So that's going to be right minus 6 minus 4 minus 2 0 2 4 6. Isn't that right? Yes. And d2y dx squared was just 2, wasn't it? Remember from the previous screen? So you can see, to go from minus 6 to minus 4, you go plus 2. From minus 4 to minus 2, you go plus 2. From minus 2 to 0, you go plus 2. Do you see what I'm doing? See, this is the rate of change of the gradient. Yes? It's fascinating, isn't it? Now look at my little diagrammatic helper here. Watch this. See, that's at x is minus 3. dy dx is minus 6. At x is minus 2, it's minus 4. At x is minus 1, the gradient is minus 2. When we've got the origin, we've got the gradient as 0. Following this pattern here, this line here. Okay, now you're going to get 2, 4, 6 for x is 1, 2, 3 respectively. 2, 4, 6, yeah, do you get that? Okay, now you can see that the rate of change of the gradient is always positive. Yes, it's positive. So that's what I'll put that big plus there to denote that the rate of change of the gradient is positive, right? Okay. Now this is a local minimum. This is a local minimum, isn't it? This point here is we've got a local minimum here. So what happens is, what I'm leading to showing you here is this. the graph is concave up. That means that's what you get for a local minimum. Now, you imagine yourself in a cave, right? And you're looking out of the cave. You're looking up. See, concave, to look out of the cave, you look up. So it's concave up. So, that way like that. So therefore, for a local minimum, I'm generalizing here to tell you guys, for a local minimum, the second derivative, in this case, and indeed in every case, is positive. Now, this is very marvelous, because in methods, what you have to do to verify the nature of a stationary point is you have to basically test the gradient on either side of that point to get a bit of a profile of what the derivative is doing, and thence conclude whether you've got a local maximum or a local minimum. But with this technique, if you want to verify whether once you know you've got a stationary point, if you take the second derivative, right? If you take the second derivative, and at the value of x where you've got the stationary point, which is 0 in this case, right? If you test the value of the second derivative there, and if you get a positive answer, you got yourself a local minimum, guys. It's a much, much less tedious and wonderful technique to use, more wonderful technique to use than that tedious thing where you've got to basically, test the gradient either side of the stationary point. So you've got another little tool in your tool chest now to use, right? You get what I'm saying? At a local minimum, where the value of x for that local minimum, if you test the second derivative of that value of x, you are going to get a positive answer. Now let's do it for the other one on the other side of the screen. This is for the y equals minus x squared, yeah? Yes. Just put a box around there, to show you the little smiley face. Smiley face shows you that he's positive, he's feeling positive, and the mouth forms the curve. So you can see, if you've got a local minimum, you put the eyes on there, looks smiley, and he's positive. So that tells you that the second derivative is going to be positive for a local minimum. Yes. Okay, let's do this one now. Y equals minus x squared. You can imagine what we're going to get, the opposite result. So there's x squared, there's dy dx, and there is d2y dx squared, which of course is going to be minus 2, right? Minus 2. So you can see now, to get from 6 to 4, we're going down minus 2 units. To get from 4 to 2, we're going down 2. To go from 2 to 0, we're going down 2, and so on and so on and so on. So in this case, the rate of change of the gradient is constant, but it's negative 2. If for every one increment in the positive x direction, you go down 2 units in the gradient, right? So there's my pictorial representation. There's the gradient at minus 3, minus 2, minus 1, 0, 1, 2, 3. See how it's going down, 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 down. Even though it's pointing in the positive direction, it goes down 2 units for the next increment in x. You see? Get it? Very good. So therefore the rate of change of the gradient is negative, so hence I've written this great big negative sign up here. That's the rate of change of the gradient is negative, and this is a local maximum, right? And this graph is concave down. Down, down, down. Okay, so you've got to look down to look out of the cave, don't you? Like this. Okay, so that's that away, right? So now you can conclude also, ladies and gentlemen, that for a local maximum, the second derivative is negative, right? And I've drawn the little man there. Watch this. There's the little man. He's feeling pretty negative, isn't he? Yes, because he's got down in the mouth, because he's a local maximum, and he's going to be negative. So the second derivative is going to be negative for him. Okay, that's a pretty marvelous new tool we've got in our mathematical tool chest now. Okay, second derivatives have a very obvious significance for local minima and local maxima. Okay, right. So summarising the local max and mins, including second derivative behaviour. Watch what we're going to do here. And we've got this, and we've got, there it comes. Now, here's the gradient, like that, and the gradient is going up. Now, do you see what's happening here? The gradient is going up. Yes, if the gradient is going up, actually, what you can do is you can look at the front end of the gradient tangent line, and it'll be moving in an upwards direction from one successive x value to the next. That's what I mean by the gradient going up. Okay? So that's, yes, the rate of change of the gradient is positive for a local minimum. Yes, local minimum second derivative is positive, and you put the little smiley face in to complete the picture, and you can work it out. Okay, it's easy. For the local, for the other one, for example, though, it's the opposite trend, right? There's the tangent lines for successive values of x, and you can see that the gradient is going down, and the way to pick that is basically the front end of the tangent line at every point at which you're taking the gradient from one successive point in x to the next one. That leading edge of the gradient will be moving in a downwards direction. You can see it is, okay? It's moving downwards with each successive increment in x. So therefore that's a negative rate of change of gradient. For a local max, the second derivative is negative. Okay? Yes, you get that. Okay, now let's have a look at all this. Oh, gracious me. What are you doing, Wolfman? No, it's all just a very nice summary, okay? So, for the left-hand side, we've got a minimum stationary point, haven't we? And for the right-hand side, we've got a maximum stationary point, haven't we? So I put M here to denote maximum or minimum stationary point. The type of gradient here, at this point here, we've got zero gradient, right, at the local minimum. Over here, we've got a zero gradient at the local maximum. Isn't that right? Okay, very good. Now, so you get a zero gradient, okay? A zero gradient. Now, d2y dx squared, the rate of change of the gradient, is going to be plus for a local minimum. Plus for a local minimum, it's going to be minus for the local maximum. Therefore, you put in this little symbology here for plus or minus. Okay, so local max or min on the original function, zero gradient for the gradient function, plus or minus for the second derivative function, the value of the second derivative at that value of x for the stationary point of the original function. Right? That acronym there is very important for you to remember, okay? MZPM. If you can think up a nice little words that go with it, please tell me, because I can't think of anything. But it's MZPM, right? Yes, I just thought of something to do with Prime Minister, but I won't say it. Okay, points of inflection. Okay, points of inflection. Now, what are these beasts? They are points where a concave up part of a function or a curve of a function meets and is joined to a concave down section. Okay, here's some examples. We've got y equals sine x, y equals cos x, y equals tan x, y equals x cubed, y equals x into x plus 2 times x minus 2, and y equals x cubed into x minus 2. Woohoo! Now let's have a look at these. I'll show you. Where concave up meets concave down. Look, this is sine x. There's sine x. Now, look at this, guys. Can you see the concave down and can you see the concave up? Well, I'll show you. There's concave down, right? That's the concave down bit. There's the concave up bit. Now, where do they meet? In the middle. Where do they meet? There is where they meet. That is the point of inflection. You seeing? You getting me? Good. Now let's do the next one, cos x. Now you're getting the picture now. You have a look. Where is concave up? Where is concave down? Where do they meet? There's concave down, right? There's concave up. Where do they meet? That's the point of inflection, and that's the other one. Okay, you get it. Tan now. Tan's a little bit more obtuse because tan's the man, and but you can see the general curvature, right? This is kind of like concave upish, but and to the left, that's sort of up. It's sort of going a bit up. Come on, yes it is. And this bit here is coming a little bit downish. Sort of there's a bulges in that direction. So if you look out of that very, very shallow cave, you'd still be looking that way, which is trending downwards, isn't it? Yeah, so that's basically your concave down. There's your concave up. And where do they meet in the middle? There, and there. Okay, they're the POIs, yeah? Points of inflection. Okay? Very nice. Okay, so what are we going to do now? X cubed. Ah, well, come on, you got it? Where is it? That's concave down, that's concave up, and that is the POI, but it's not only a POI, this is a celebrity POI, this is a stationary point of inflection because the gradient is 0 at that point of inflection, in addition to it being a point of inflection. So it's a double trouble. It's stationary as well as being a point of inflection. Get it? Good work. Now this one here is our S-bend cubic, right? Well, that's a pretty easy one, isn't it? Where's concave down? There it is. Where's concave up? There it is. And where is the POI? There it is. Yeah? My oh my, POI. Let's do the last one now. Okay. Okay, we've got a wobbly looking quartic there. Okay, now this is very interesting, guys, because there's a bit of an intricacy in this one. I can spot actually 2 concaves up and 1 concave down. Can you? Can you really? Well, I'll show you. There's a down. There's a down, okay? And that's concave down. There's the ups, right? There's the ups. So that means we're going to have 2 points of inflection there, aren't we? Yes, because there's 2 boundaries between concave up and concave down, isn't there? Can you spot them? Can you spot them? Come on, it's not that difficult, or it's a little bit more difficult than the previous ones. Okay, there's your concave up. Now there's 1 POI, yes. I think you spotted that one, didn't you? Where's the other one? It's where this concave down meets this concave up. So it's got to be about, probably about there somewhere, do you think? Oh, I forgot to mention that was a stationary POI, a celebrity. Yes, stationary POI. Did you get that as well? Good. And this is your other POI there. Yeah, you sort of got that, didn't you? Great. Now, we're going to trace the tangent line from left to right, and I'm going to show you the trend. The trend is your friend. As the gradient decreases, the tangent line direction changes so that the front end moves down, right? As it decreases, the front end goes down, right? As the gradient increases, the tangent line direction changes so that the front end moves upwards, and at the point of inflection is the boundary between both of those different trends, as you will see very dramatically in a moment. Now I've got just a nice little curve here for you. Now you watch. Okay, we're going to move the tangent line along, increment x in stages, and you watch what happens. Now the gradient is decreasing and the front end of that tangent line just moved down a little bit. Now watch again. See? Moving down as the gradient decreases. Moving down some more, moving down some more, moving down some more, moving down some more. Now we're nearly at the point of inflection. Do you know where the point of inflection is? You do, don't you? A little bit more now. I think we're nearly there. Okay? There it is. Now, what's going to happen now? Because the gradient is going to start increasing now. So the front end of that tangent line is going to start moving, not down anymore, but up. Oh, look at that. Isn't that something else? Yes? Now you can see the trend is your friend. Do you get it, guys? That's what happens, okay? Now, at the POI, the second derivative is 0. So the rate of change of the gradient changes sign from positive to negative, or from negative to positive through the point of inflection where it is in fact momentarily, for one single value of x, 0. Okay? Yes, so at the POI is the point at which the rate of change of the gradient is instantaneously at 0. Okay? Now, to illustrate this, let's take a sine graph, okay? There's a sine graph. Now we're going to do a table of values to show you what goes on here. There's concave down, concave up, and a POI for you. Do you see? And there's a few of them along the way, really. There's another one there, if you like, but we're not going to use that one for illustration purposes. And actually there's another one here. They're all over the place in sines and coses, and tans for that matter. Yes, there's 0 pi, 2 pi for sine. Now, this is a fairly small table of values. I apologise for the smallness of it, but you're going to get the idea in a moment. I'm just going up in increments of pi on 4, so basically x, I'm doing x, I'm doing 0, pi on 4, pi on 2, 3 pi on 4 pi, 5 pi on 4, 3 pi on 2, which is 6 pi on 4, and so on, right? And we're going to do the value of d of y, dy dx, and d2y dx squared, okay, for sine x, yeah? So let's do that. So what is sine of naught? Well, and sine of pi and 4, and so on and so on. You know what they are, yes? Okay, there they are there, in all their glory for you. Now, what about dy dx, which is going to be cos x? Okay, so what's cos of naught? It's 1. What's cos of pi on 4? What is it? It's 1 over root 2, isn't it? What's cos of pi on 2? It's naught. And so on and so on. What's cos of 3 pi on 4? It's minus 1 over root 2. Cos of pi is minus 1. Cos of 5 pi on 4 is again minus 1 over root 2. And cos of 3 pi on 2 is 0. Yes? Now that's dy dx. That's the gradient of sine x. Those values are the exact values of the gradient of sine of x at those x values illustrated up there in that table, right? That's what they are. Now we'll do the second derivative now. Okay, so here's the second derivative. Now that'll be the derivative of cos x, of course, is minus sine x. So that's the second derivative of y equals sine x, okay? So it's basically just the negative of these values up here. It's just going to be the negative of those values of sine x, yes? Okay, so let's put those in. That'll be naught minus 1 over root 2 minus 1 minus 1 over root 2 naught plus 1 over root 2 and plus 1. Now, guys, these are the values of the second derivative, all right? They are the values. They are the rate of change of the gradient of sine x, all right? Now, let's just have a look at this, the rate of change of the gradient. Now, this region here is where the rate of change of the gradient is negative, right? This region here is, and beyond actually, is where the rate of change of the gradient is positive. And look, there, at that point there, the rate of change of the gradient is 0. Now that's got to be a point of inflection. And is it? Is it? Where it's pi, oh, apple of my eye, it's a POI. Isn't that sensational? Now, there's more. Wait, there's more. Okay, it's negative there. It's negative there. Now, watch the graph. Look. You see, from here, around here, it's becoming, the rate of change of the gradient is negative, and it's most negative up here, where this curve is the steep, you know, that's changing the most, right? And then it's tapering off, less negative, but nevertheless still negative, and then it just peters out to the POI where the rate of change of the gradient is actually 0. Now, I've got more for you. There's the 0 point, that's the POI, and I've denoted that there for you. Okay, that's where the rate of change of the gradient is 0. Now, in the other section, this section around here, the rate of change of the gradient is positive. And have a look at the graph. There it is. Similarly, it starts to get more positive, increasingly more positive. Most positive here, then starts to taper off again until you get over here, which is your next POI. So, look, it all makes sense. It all makes sense. Yeah, it's just quite, yeah, that's a POI, etc., etc., etc. Yes, so at the POI, the rate of change of the gradient, d2y dx squared, is 0, and it changes sign from positive to negative or vice versa. Okay? Okay, I know, it's sensational. And also the rate of change of the gradient is at a maximum at the local max or minimum, okay, as the diagram at the left shows. See, it's the rate of change of the gradient is actually the most at this point here, where you have a local max or a local min, right? Okay, next screen. What do we got here? The relationship between the POI and the gradient of a function. Ah, very interesting. Let's have a look at this. At the POI, the gradient has a local maximum or a minimum. The gradient itself has a local maximum or minimum. So this is very interesting. Now have a look at that. You've got a, what do we got there? A quartic. We've got a cubic, which is the gradient function there. So we've got the quartic function, the cubic gradient function there. Now you have a look at the POIs. Where can you spot the POIs on the quartic up here? Come on, where's the concave up? Where's the concave down? Yeah, so where are the POIs? They're at the boundary between where they meet. Yes, there they are. Now, okay, yeah, now they coincide. What I'm saying here is they coincide with on the gradient function, they coincide with a local maximum or minimum. Have a look. See? That's a local max on the gradient function, right? So basically, yes, the gradient has a local max at the POI, and the gradient there has a local min at the POI. That's what I'm trying to say, okay? Yes, I know there's a lot to take in this session, but you'll need to look at it a couple of times to really get it all, because there's a huge amount of conceptual material I'm covering here. That's all right, you'll get used to it. Now over here I've just got another example for you, another quartic, but this is a wobbly quartic with a stationary point of inflection here, right? Stationary point of inflection. So where are the concaves up and concaves down and all the rest of it? Yes, now, so where are the POIs, the boundaries? Yes, there's one, there's the other. So they should coincide with local max and minima in the gradient function. And do they? Yes, that's a local max, even though it's a stationary point POI. Okay, it's still local max, it just basically just comes up to this point here. The gradient doesn't actually get to be positive, it's negative, comes up to the POI and then goes back and becomes more negative again, right? And this other POI over here, we've got a local min, haven't we? See, isn't it marvellous? It's just something else, this stuff. Right, now, the gradient trend, what have I written there? The gradient trends towards a point of maximum, so to explain the local max in the gradient function, the gradient actually trends towards a point of maximum steepness, right, at the POI, and then reverses the trend past the POI as the gradient then trends in the opposite direction. That's why you get a local max, because the steepness is the most, in a local sense, at the POI before it starts to reverse the trend and go back the other way. Alright? This accounts for the local max or min in the gradient at the POI, okay? Now, summary. Here we go. I think we're near the end now, and the end is going to be our friend here. Alright, so here's, oh good, we've got a triple graph here, triple banger. This is the function, this is the first derivative, and this is the second derivative, alright? For this particular... What are we doing again? Hang on, I'm getting lost. Between the function and its first and second derivative. Yes, alright, that's good. Now, just go with this. We've got POIs there. You know that now, don't you? Okay. Now, here's the gradient function. We've got, they coincide on the gradient function with local max or min. Alright. Now, right? And at a POI, as I've already told you, through this course of this video, that at POI the rate of change of the gradient is what? 0, right? So you get a 0 point there on the second derivative function. Now that's really, really important. That's the whole picture coming together there now in this summary page. So that's my little acronym I use. Point of inflection on the original, local max on the gradient, 0 on the second derivative. I call it poems, okay? Poems. And it's if you can remember that acronym, you'll be very, very, very well off in terms of your understanding and your ability to recall all this stuff. Now, here we go. Here's another one. Now, this is basically another example, okay? So, what we've got there is we've got local max and min now. Yes, this is the local max and min of a function, not the point of inflection. I'm just dealing with local max and mins here to show you what happens with that one and the first derivative and the second derivative, which is what I was alluding to at the start of this video. So we've got local mins and local maxes. Okay, now, you know that a local min and a local max, what happens at the first derivative? Well, it's a stationary point. So you get a 0 point, yeah, to denote that the gradient is 0. The gradient function, yes, first derivative. Now, remember at the very start of the video I told you when you get a local min or a local max and you take the second derivative, well, what happens? You get a positive if it's a local min. Remember I talked about the smiley face at the start of the video. You get a positive. For a local max, you get a negative, right? Okay, so that's, yes, mins coincide with plus and max coincides with minus on the second derivative, okay? Yes, there, that's the plus, the smiley face for the plus, gets you a plus second derivative. the frowny face for the local max, where you get basically a negative, so you get a frowny face for the second derivative, yeah? You get the minus for the second derivative, so I'm making it into a frowny face, okay, to say that he's negative. Now the acronym for this is basically, okay, MZPM, okay? MZPM. I was thinking before, my zero Prime Minister. That's if he didn't like the Prime Minister. He could think of that in Australia, but, you know, maybe that's a bit unkind. I don't want to be unkind. So, okay, so look, I've set it out all there for you. This is the trend for points of inflection give rise to maxima and minima on the first derivative. On the second derivative, you get a zero. If you're just dealing with max and mins, on the first derivative you get zeros. On the second derivative, if it's a local minimum, you get a plus. If it's a local maximum, you get a minus. Okay? Now that's pretty important. That's summarising everything, bringing it all together for you, right? Now there is a bit of an exception here. I've got to show you something. Now, NB, oh yes, NB, nota bene in Latin. The poems thing does not always work in reverse, okay? So what am I saying there? This all works in reverse. This one has got a bit of a problem. It works here, but it doesn't work here. So, Wolfman, what do you mean? Well, I'll show you what I mean. I'll show you what I mean. I'll give you an example. If you had the graph of, say, y equals x to the 4, okay? Now, the first derivative is 4x cubed, right? And the second derivative would be 12x. Now, okay, we've got a second derivative where at the stationary point, you've got a stationary point there. That's the classic U-shaped graph of a quartic, right? You've got a stationary point there, and the second derivative is 0, and that, my friends, but unfortunately the second derivative is 0, but that ain't no point of inflection. In fact, I should say it isn't any point of inflection. So there's a problem, okay? So if you have, what I'm trying to say to you is, if you have a second derivative which is 0, which in this case it is, this is not a point of inflection. So you can say that if you have a point of inflection, yes, it's going to go yes, therefore this, you'll get a 0 second derivative. But if you have a second derivative, it doesn't necessarily mean that that is going to be a point of inflection. That's what I'm trying to say. Do you get what I'm trying to say? Because that second derivative is 0 and it's not a point of inflection. I'll show you the graph, okay? It's not a point of inflection. See, there's the graph there, right, of y equals x to the 4th. So that's the second derivative is 0, but it's not a point of inflection. So that's where the poems thing only works POI to m to z, but it doesn't necessarily work from z to m to POI in terms of a logical progression of thought. Are you getting that? Yes, so you can go that way with the poems, but you can't go necessarily that way, from z to m to POI. All right? Good, good, good. Now I think we're up to the very last screen now, a table of shapes. Yes, this is gradients and second derivatives. This was a very long session, but it's a very useful and very interesting session. A table of shapes, gradients and second derivatives, the relationship. Now, okay, we've got on this down here, we've got the gradient or the first derivative. I'm just looking at shapes, right? And along here we're going to use second derivatives. Now, okay. So I've got a positive gradient there, which means that the slope is going to be doing that. I've got a 0 gradient there, which means the slope is going to be doing that. And I've got 0 gradient there. Did I say 0? I meant negative gradient there, where the slope's going to be doing that. 0 gradient here, where the slope is going to be flat at the point of 0 gradient. Over here, I'm going to be dealing with second derivative positive, second derivative negative, and second derivative 0. Now, I want you to tell me, or to draw a shape on the page that you've got near you, and holding your trusty pen and looking at the page, I want you to draw the shape that you would get, where the gradient is both positive and the second derivative is also positive. So the gradient is becoming more positive. Okay, what are you going to get? What are you going to get? What shape are you going to get? You got it locked in? Here it comes. There. You get that? Now, what about over here when the gradient is negative? Okay. Oh, no, I don't mean that. I mean the gradient is positive, but the rate of change of the gradient is negative, right? You got it? Have you? There it is. Yes? Now, what about when the gradient is positive, but the second derivative is 0, okay? So what does that tell you? The gradient is positive, but the second is, if the second derivative is 0, in all likelihood you've got a, you're going to have a point of inflection, aren't you? Yes? Yes, okay? So that's going to look like that. That's one way of doing a point of inflection, where it's concave down here, concave up there. This is another one where you've got a concave up there and concave down there, okay? And this is the POI there and the POI there, right? Are you getting the idea of this game? Okay, now we're going to do the whole same thing again for negative gradients, okay? Now, I want you to pause the video and I want you to fill in the rest of them, and then you can come back and I'll show you, okay? You ready? Go and pause the video now and do them, and then you can come back and see. Okay, you're back? Alright, here they come, right? Da-da, 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 and da-da, da-da, da-da. These last ones, this last row here means just at this point, just at the point where I put the little cross. Okay? Did you get that? It's very important that you're able to conceptualize this, because it helps you to fill out and complete your understanding of what I mean by second derivatives, yeah, and the implications of the shapes of the functions for various scenarios such as I've given you here. Alright, I think that's the end of it. Yes, and you're a star and you'll go far if you do plenty of practice. So, if you're a little bit unsure, you better go back and have a look at this video. It's an extremely pivotal watershed video in the whole area of second derivatives, okay? And we'll see you next time. Okay, bye.